Welcome back, everyone. We're going to be solving LeetCode 997, Find the Town Judge. So in a town, there are n people labeled from 1 to n. There is a rumor that one of these people is secretly the town judge. They tell us the town judge exists, or if the town judge exists, then the town judge will trust nobody, and everybody except for the town judge trusts the town judge. And there is exactly one person that satisfies properties 1 and 2. So we know from the statement we are going to return, or there is going to be one person that is the town judge. And we are given an array called trust, which represents that the person labeled A trusts the person labeled B. And if a trust relationship does not exist in our trust array, then such a trust relationship does not exist. And they want us to return the label of the town judge if the town judge exists and can be identified. Otherwise, we're going to return -1. Okay, so this is a graph problem. What we are given is an array of relationships, trust relationships, right? And they tell us A trusts B. So what we're going to have to do right off the bat is build an adjacency matrix, or an adjacency list. So let's do that. We'll say graph is going to be equal to an empty dictionary, and we will loop through our trust array. So we'll say for we'll say element for element in trust. We're going to destructure it, so we're going to get A and B like so. And before we go any further, we know that there are n people labeled from 1 to n, right? But they won't necessarily be inside of our trust relationship, right? So what we have to do is add all of these people to our graph before we can add our trust connections. So how do we do that? We can just say for I in range 1 to n plus 1, we are going to say graph of I is going to be equal to an empty array. All right, that'll give us all of the people from 1 to n, and then if there exists a trust relationship between two people in our trust array, then we can just add that to our graph. So once we've added the people, now we can loop through our trust array and add those relationships to our graph. So we've got the element, we've destructured it. Now we have to check. If A is in our graph, then we want to say graph of A dot append B, right? That will give us our trust relationship. So let's print out our graph to see what we're working with. Right, so this gives us a graph where person 1 trusts person 2, and person 2 trusts no one. So from this alone, we can deduce that 2 is the town judge. And indeed, in example 1, right, they give an output of 2, right? 2 is the town judge because person 2 trusts no one, and everyone else within our graph trusts 2. So now that we have our graph built and our relationships added, how do we find the town judge? Well, we know the town judge has to, if there is a town judge, they're going to have no trust relationships, right? They won't trust anyone. So what we're gonna have to loop through our graph. So we'll say for person in graph, we want to say if the length of the array of that person is equal to 0, then we can check off one of these conditions, right? The town judge trusts nobody, but we also have to satisfy a second one. So let's write this first one first. So we'll say for person in graph, if graph of person, if the length of that is equal to 0, then we have satisfied one of the two conditions. Now, how do we check the other one? We have to check and make sure that every other person in the graph also trusts the town judge. In order to do that, we can keep track of the counts, right? That's probably the easiest way. We could have a counts dictionary, we'll say counts is equal to a default dict. And whenever we run into this in a trust relationship, right? So if we run into 1 trusts 2, we're going to increment the 2 variable by 1. So when we check for every person in graph, right, we've satisfied the first condition. Now, how many people trust 2, right? That's going to be represented in our counts dictionary. So there should be 1 person who trusts 2. So whenever we access 2 in our counts dictionary, we should get the length of our graph minus 1. And that will tell us if that person also satisfies the second condition. So we'll say we have to add these counts to our counts dictionary first. So we'll say counts of B plus equals 1. Right? Now we can also check that second condition down here. So we'll say for person in graph, if the length of the person of the graph of person is equal to 0, right here, satisfy 1 condition. Now we have to check and counts of person is equal to the length of our graph minus 1. So for example 1, right, the length of our graph is 2, right? We have 2 keys. Now, if we're at person 2, for example, we would index into our counts dictionary, right, and we would see that this value is equal to 1, and that is indeed equal to the length of our graph, which is 2 minus 1, which is 1, right? So then we can deduce that it does satisfy the second condition. If both of these hold, then we can just return the person. Otherwise, they tell us we can return -1. So this is looking pretty good. Let's run this. And it does pass all 3 test cases, so we'll submit. Perfect, it does run. So, time and space complexity. Time complexity is going to be O of n for this. Space complexity is going to be based on the length of our graph plus the length of our counts dictionary. So we could say counts.length plus our graph.length. All right, that'll do it for LeetCode 997.